if you could all mute yourselves for the meeting, might help us out. Atreya Manaswi is from Orlando. He is doing some incredible research on hive beetles, and he's written a book, the Bee Book. It's out there on Amazon. We'll discuss that a little bit later too. Atreya, thanks for showing up and sharing your knowledge with us. This is a good talk. A lot of us don't deal with the hive beetles. I've seen 3 beetles in all my hives. I've seen more larvae in my hives. So knowing a little bit about the birds and the bees, the larvae had to come from somewhere, or the birds and the bees and the beetles. So the larvae was there. But I guess, Atreya, if you're ready, I'll hand things over to you.
Absolutely. Thank you so much for that introduction. So I hope you're all able to see my screen.
Yeah.
Okay, great. Okay, so good evening to all of you. My name is Atreya Manaswi. I'm a 10th grade student at Orlando Science High School in Orlando, Florida. And I've been working with the University of Florida and also the USDA for the past 4 years since the 7th grade. So I'm going to be speaking to you all on small hive beetle biology and control tonight and sharing some of my research using organic trapping agents. So before I actually get into my presentation, I'd like to just take a moment to explain my backstory of how I really got into beekeeping at such a young age. So roughly 4 years ago, I went on a short fishing trip with a friend and his grandfather who was a beekeeper. And while we were on the boat, my friend's grandfather began telling us stories about his beekeeping practices and how decades ago he would collect dozens of barrels of honey, but how that season he'd gotten merely 3. This was very shocking to me, and I went home and dug into the statistics and research and did some brainstorming and really realized how important bees are to all aspects of our lives. I began my first year of research in the laboratory at the University of Florida in the 7th grade, which is the picture from the top right. And then in following years, I set my foot into the fields, which is where I really came to understand the hardships and the values of beekeeping. Now, for my presentation tonight, I'd like to focus on 2 principal components. The first is the biology of the beetle, so discussing the background, morphological characteristics, behavioral and social characteristics. And then the second aspect of this presentation will focus on treatment, so chemical-based treatment and then also organic-based agents. The takeaways I would hope for you to have by the end of this presentation are firstly, what small hive beetles are. Secondly, what small hive beetles do to your bees and what they do inside the colony. Third, what I discovered from my research. And then lastly, how you can apply my research findings into your hobbyist or your commercial beekeeping practices. So without further ado, I'd like to begin with the biology. Now, the scientific name for this beetle is Athena tumida, and they were actually native to sub-Saharan Africa prior to the 1990s. However, in 1996, we saw an infestation, or rather a report in the Carolinas, and then the first official infestation was reported in my home state, Florida, in 1998. And ever since then, this beetle has been spreading all across the globe, wreaking significant negative impacts on the beekeeping industry. Now, this beetle causes damage inside the colony. Specifically, the larvae are a major cause of the damage. They destroy honey and pollen stores, and they damage cappings and comb, which ultimately stresses the colony. This is a picture of an adult small hive beetle. So on the bottom right is an image of sexing the beetles as shown. And what you can actually do is take the abdomen of the beetle and squeeze, and one of 3 things happens. The first thing that can happen is a short appendage shoots out or nothing shoots out. The second thing that can happen is a very long appendage shoots out. And then the third thing that happens is that the beetle explodes because you squeeze too hard. Now, assuming that the first thing happens, generally that indicates that the beetle is a male. So that short appendage is a phallus. Now, that long appendage that shoots out is actually an ovipositor. So this indicates that the beetle is a female. This ovipositor of the female, this long appendage, shows that, or essentially its ovipositor functions as an egg-laying machine gun. So the female beetle is able to take her ovipositor and then deposit eggs into cracks and crevices within the hives, which the bees can't actually reach into, which is suitable for their reproduction. And that's the male and that's the female. Now, there are also other types of beetles that can show up in your colonies. On the left here, I have a pollen beetle and a sap beetle. I show these images to show that just because you have beetles that show up in your colonies doesn't necessarily mean that you have a small hive beetle infestation. These beetles differ in their color and then also their sizes. So the best thing is to probably call your local bee inspector or to just take one of these beetles and compare them side by side with an image of a small hive beetle. Again, it's not always a cause for concern if you see other beetles that show up in your colony. This image on the right here is of what's called a large hive beetle. These large hive beetles are obviously larger in their size. This specific species is endemic to Africa. Now, contrary to the small hive beetle, which has the scientific name Athena tumida, large hive beetles are a broad class. They don't have a specific species. Rather, each different region has their own assortment of these large hive beetles. And as you can see, this large hive beetle is 20 to 23 millimeters in length, whereas small hive beetles on average are 4 to 6 millimeters in length, so about 4 or 5 times smaller. Now, there are 4 primary stages in the life cycle of the small hive beetle. The first stage is the egg stage. So it takes 2 to 4 days for these eggs that are laid by the female to hatch. After this stage, they enter the larval stage. And this larval stage lasts from 7 to 10 days. After the larvae have stuffed themselves, they exit the colony and then pupate in the soil, this bottom right image, which takes 3 to 6 weeks. After this 3 to 6 week period, they emerge as adults and develop this reddish brown hue in 24 to 48 hours afterwards. Now, something important to note is that given optimal environmental conditions for their reproduction, let's look here, we have 2 days for the eggs, 7 days for the larvae, and then 3 weeks for these pupae. 2 plus 7 days is about a week, plus this third week is 4 weeks. So it takes 4 weeks for this beetle to hatch from its eggs to develop into a fully matured adult, 4 weeks for that. And the lifespan of this beetle is 24 weeks. 4 times 6 is 24, meaning that given good environmental conditions, we can see up to 6 consecutive generations of beetles inside a colony at a given point, which really shows that these infestations can get out of hand if not controlled. Now, as I mentioned, the larvae are the root cause for most of the damage. They appear very suddenly and often in large numbers. Now, there's this yeast associated with the feces of the larvae that causes fermentation of the sugars present in pollen and honey. This yeast is called Codima omerate, shown in the bottom left. These larvae defecate as they're feeding throughout the colony, and this yeast is introduced, which causes that fermentation. Now, that fermentation causes the release of a volatile compound called isoamyl acetate. So when isoamyl acetate is released, it essentially serves as a calling signal to other beetles in the vicinity of the hive and tells them that there is a surplus of food here and that they should come to their region. Now, when this event occurs, what you see in the middle image, it's termed a slime out. The brood rearing ceases rapidly and the population dwindles. In fact, the bees can just abscond or leave the hive entirely if conditions are bad enough. And the presence of these beetles is actually a marker in CCD, or colony collapse disorder, which you may have heard of or witnessed inside your hives. There are really 2 telltale signs of a larval infestation that is this bad. The first thing is that when you pop open the super, or rather the lid on the super of your hive, you'll smell a rotting citrusy odor. And the second thing that you'll see is honey bleeding out from the front of the colony, as you see in this image on the bottom right. And unfortunately, when the colony gets to a stage that's this bad and the larvae have taken over, there's really not much that can be done to revert this. To discuss some of the behaviors associated with the small hive beetle, an interesting one I'd like to note is something called the jailing phenomena. It's not an official term, but I'll describe what it means here. So the honeybee is actually able to corner these beetles into cracks and crevices within the colony. So you have these guard bees that are pushing these beetles into these edges of the hive, and essentially patrolling them to make sure that they don't wander around freely in the colony. Another interesting behavior is in the bottom right, it's shown. The beetles can actually take their antenna and antenate against the mandibles of the honeybee, causing the honeybee to regurgitate food and feed the small hive beetle. So what's happening here is the beetle is tricking the honeybee into thinking that the small hive beetle is actually a bee, and therefore the bee is feeding the small hive beetle. So this doesn't occur that often, only about 10% of the time, but it is an interesting phenomenon and really shows how cunning these beetles can be. Another thing I'd like to discuss is the differences between wax moth larvae and small hive beetle larvae, because at first glance, they do look comparable. So for wax moth larvae, they are covered all around their body with long hairs. They have 8 prolegs here in the back and then also 6 legs near the head. The most distinctive characteristic, obviously, is the webbing and cocooning that you see with these wax moth larvae. Whereas with small hive beetle larvae, these beetle larvae are much smaller, about half as long and then a quarter of the width. They also only have 6 legs near the head. In addition to this, these beetles have much more pronounced abdominal segmentation, and they also defecate in the colony, resulting in that slimy situation, the slime out that I discussed earlier. Some good apiary practices in general for small hive beetle infestation management are that when combining comb, you should be careful because you can actually introduce eggs that are present inside a frame into another colony. Also, when removing old frames or hives, especially with rotten, cracked, or damaged comb, anything dilapidated or broken up, it can make for very good hiding spots for beetles. So removing these frames and then putting them into another colony, again, it's risky. Also, when pulling honey from the colonies, it's important to extract very quickly, preferably within a 2-day period. If not, the alternative is to freeze your honey to prevent those beetle larvae or the adults from actually taking off the cappings and then feeding and defecating inside the honey stores. Another thing that you can do is exposing your hives to sunlight. So small hive beetles are repelled by the sunlight, whereas the bees don't mind as much. They are a little bit aggravated, but it's a good management strategy that's also pretty easy to implement. The last thing is that with nukes or also adding new supers or new frames, especially with nukes, whenever you're adding these new frames or new supers to nukes, the bees may not be able to patrol the frames or the supers that you're actually adding into the colony, especially with a weaker nuke. And this leaves those beetles more free to roam around and place their eggs inside the colony. So only adding as many frames or supers as needed as you're seeing the colony grow and progress. Now, transitioning over to the second part of this presentation, to the chemical treatments. So there's 2 main chemical agents that exist on the market for small hive beetle treatment. The first is Checkmate Plus strips. So these are a 10% Comofos strip and they're pre-coated. So they're placed inside of the hive, and whenever the adult beetle comes in contact with this, either through dermal contact or ingestion of this chemical, then it begins to die. The other agent is Guard Star. So this is a soil drench. It has a 40% active permethrin concentration, and it's targeting the pupae of the small hive beetle. So if you're curious, both of these chemicals actually function as acetylcholinesterase inhibitors. So basically, they're affecting the central nervous system of the insect. Acetylcholine is a neurotransmitter in the nervous system, and these chemicals essentially they prevent the breakdown of that neurotransmitter. And this causes hyperactivity, paralysis, tremors, and then subsequently death in infected insects. Now, as I mentioned, Comofos is applied in stages 1 and 2 when the beetle is an adult. The beetle comes in contact with it and then dies. The permethrin is applied in stage 5, the pupae stage. Coming to the non-chemical or organic and biological treatments, there are a few that do exist. So the first of which is diatomaceous earth. So diatomaceous earth is placed around the colony, and it targets the small hive beetle by essentially drying out its cuticle, which eventually kills it. Another thing is these nematodes on the right. These nematodes, there are many strains of nematodes that exist, but these specific nematodes that target small hive beetles are termed entomopathogenic nematodes. So these nematodes essentially are released inside the soil and then enter the beetle through an orifice, either the mouth or the anus, and then enter the gut of the beetle where they work as a parasite, eventually killing the beetle from the inside. Another popular thing is baseboard traps. The agent that I used, or rather the trap that I used in my study, was these beetle blaster traps that are shown here. These beetle blaster traps are a common thing that's used in the industry, and they have attractants inside of them. So these are commonly like oils or apple cider, which is a very common thing to use. How they work, if you're not familiar with them, is these beetle blaster traps are placed in between the Langstroth frames of the colony, and then the beetles that are already inside the hive are attracted to the treatment solution or attractant inside of that trap, and they fall in through the slits at the top. These slits are only so small so that the beetle can come through and the bees will not enter these traps. Now, to discuss some of the advantages and disadvantages of the chemical treatments that exist, the chemicals are very effective and they show fast results, but they do have a lot of disadvantages. The first is that they can become extremely unaffordable, especially on a large scale. Another thing is that they risk soil, water, and contamination to the hive and also the environment. They also pose many health risks. I'm a big believer in organic treatment practices, and my research explored these organic agents. So what I discovered was an affordable and sustainable treatment that has virtually no environmental consequences. And so my research can be broken down into two primary phases, or 2 years. The first phase was testing 7 inorganic and inexpensive small hive beetle treatments. So these were evaluated through a field trial. And then the second year took the best agent from this first year, and of these 7 agents in year 1, beer was shown to be the best treatment by far. So in year 2, I was essentially taking beer and then refining it in the laboratory and creating a blend based off beer and then testing it. So to begin with phase 1 or year 1, in year 1, I looked at 7 organic agents. So these were apple cider vinegar, mango puree with boric acid, cantaloupe puree with boric acid, yeast, peanut oil, grapeseed oil, and beer. So these agents were chosen specifically because the literature has shown that this beetle can fundamentally feed and reproduce on tree sap, rotting fruits, and such odorous compounds. And based on that hypothesis, these agents were chosen. Now, this image in the bottom right shows a beetle blaster trap that has the cantaloupe puree inside of it. All of these black specks inside are beetles that have been killed. This image here of me on the left is of me working in the field trials with my beekeeping suit. You might be looking at this picture and thinking, what a responsible young beekeeper, right? Well, no, that's completely incorrect. I was stung dozens and dozens of times while in the field, sometimes even in the feet, in the arms, on the chest. It was a very painful and eye-opening experience for me, and really taught me about the hardships that go into beekeeping. Again, a very eye-opening experience for me. So each week, I would take these traps that had the treatment solution inside of them, and I was running experiments for a 6-week period on 24 honeybee colonies, so a very large field trial. Each week, I would take these traps with the treatments and then place them inside of the hives according to a randomized schedule. Then I would leave them in for a week. And then the following week, I would come to these same hives, extract those previous week's treatments, and then replace them with fresh bait. So I did this each week, this constant cycle of replacement and then extraction, or rather extraction and then replacement. And this way I was able to place fresh baits inside of the hives each week and see how the treatments were performing throughout the course of the 6-week study. Again, this was a randomized trial. So each week I was placing these traps in different locations, or rather in different hives, to account for bias in the beetle populations of the hives. Essentially, if one hive had a higher beetle population and another hive had a lower beetle population, then each week I would be rotating the treatments to account for that. This image in the middle here is of me counting the beetles. And this was done in my mother's kitchen, actually. This was 2020, the year of the pandemic. So she wasn't all that fond of this idea because all the commercial laboratories were closed, but this is the only option that I had. I remember sometimes we had loose beetles in our household. These beetles can fly, by the way. So my brother and I would have fishnets in hand trying to catch loose beetles around our household. That was one of my fondest memories from my research. After all of that extensive data collection, I ran rigorous statistical analyses. So this was one of the tests that I ran. What's important to note here is that this test is essentially comparing apple cider, which was essentially the control of this study, the organic standard that beekeepers are using, against the other agents. So here we can see apple cider being compared against mango, apple cider being compared against cantaloupe, apple cider against yeast, and so on and so forth. What's important to note is that each of these columns that has this orange arrow was significant. So what I mean by this is that this column here that has the orange arrow with apple cider versus mango, mango was shown to be significantly different in its beetle capture from apple cider. Cantaloupe puree was significantly different from apple cider. Yeast was significantly different than apple cider. And then beer was significantly different than apple cider. So this means that there was a large difference between the beetle capture or the efficacy of these two treatments. Now, this was another statistical test that I followed up to that previous test. And essentially, looking at this graphically, what the stats showed was that beer was the best treatment by far. You can see this on this Pareto chart. Each of these bars represents the raw beetle capture for each of the agents. You can see apple cider here. It has a capture of 11 versus beer, which has a capture of 198. So beer is a lot more effective. The interesting principle associated with this Pareto chart is something called the 80-20 rule, or the Pareto principle. And it basically states that if you start at this 80% mark, then trace horizontally, and then down vertically at this Pareto line, there's two segments here, one on the left and then one on the right. So this segment here on the left, 20% of what's on the left accounts for 80% of the entire population. So once again, 20% of the beetle capture of beer, cantaloupe, and somewhat, to some extent, peanut oil, 20% of these accounts for 80% of all the beetles captured in the entire study. And that really shows the significance of beer, especially compared to the other treatments. This is the box and whisker plot. Again, to visualize the data, beer here has this X that's circled in red. That's the mean, the average number of beetles captured throughout the course of the 6 weeks. You can see this X for beer is much higher than any of the other treatment means, which shows that beer was higher in its consistency of beetle capture throughout the course of the study. Ultimately, the conclusions from phase 1 was that beer was 33 times more effective in its beetle capture than apple cider vinegar, and it was the most effective treatment by a far margin. Beer costs nearly 5 cents per hive on average, and it's also widely and readily available. It does not harm the bees and only the beetles. So I assure you, using this will not render any of your bees drunk. You won't have any drunk bees wandering around in your colony. Now, if you didn't believe me on the efficacy side of things, I'd also like to show you the economic aspect. So this is just an image from Walmart.com. Miller High Life is the beer that I used. It was used because it's inexpensive and readily available. But you can see here, the cost of this is 7.3 cents per fluid ounce compared to apple cider vinegar, which is 20 cents per fluid ounce. So beer is a third of the cost and also 33 times more effective. So it's also better economically, and also its efficacy is better. Now, coming to phase 2, in this project, essentially the goal was to develop a blend based on beer's chemical composition. So creating a refinement of beer in the form of a more concentrated solution. And there were 2 research goals in mind. The first research goal was to make this blend even cheaper than beer itself. And the second goal was to make this blend even more effective than beer. And so let's discuss how I went about doing this. The first step in this process was actually extracting the chemicals from the beer. And these chemicals are called volatiles. These volatiles are just compounds that evaporate very readily at room temperature. So here, this beer bottle is connected to an adsorbent. So I'm holding this white tube here that's called the adsorbent. And that adsorbent is connected to a tube that runs through a vacuum. So when this vacuum is turned on, air is pulled from this beer bottle and then trapped inside the adsorbent and stored there. So this adsorbent's molecular structure is able to capture those compounds inside of it and keep them there. So those were the collections done from beer. And those samples actually had to be analyzed after that. To actually analyze them, I used GCMS, or gas chromatography mass spectrum. And that's a mouthful, but essentially what this instrument does is analyze the chemical composition of the compounds, and a reading is produced in this GCMS. So how the GCMS actually works is once the samples are introduced, the chemicals begin to separate in a long coil based on their molecular weight. And at the end of that coil is a detector. So this reading is generated, and this x-axis here is time, the y-axis is abundance. So the compounds that show here towards the left of this chromatogram, or this reading, are the compounds that weigh less. They are carried more easily through that coil and reach the detector first, which is why they show up here on the left of the reading, where time here on the x-axis this way is quicker or faster. So they're showing up at a lower time. Now, it's these compounds on the left of this spectrum that are important because they are carried more easily in the air and are more fragrant. So they would be more suitable for a blend compared to these heavier compounds that sit on the right that wouldn't be carried so easily in the air. They would sink. Now, after identifying potential compounds, I tested them in electroenterographies, or EAGs. This is where I could take the antenna of the small hive beetle, excise it under the microscope, and then essentially see how the beetle was responding in the laboratory to specific volatile compounds. So it was a very interesting process. And after this, I synthesized 2 blends in the laboratory. One was an oil-based beer blend, and then the second was a water-based beer blend. And so when I mentioned these blends, there were 4 specific volatiles that were used in these blends. So I wasn't just using beer itself. I was taking specific compounds from beer that I thought would be attractive and then concentrating them in a blend. So this image on the right here shown is of that oil-based blend in the field. So all of these black specks are beetles, and it has a very high beetle capture, as you can see. Again, I ran a variety of statistical tests on the data. For this year 2 project, I was running it at 3 different sites for 8 different weeks, and there were a total of 28 hives, so a very large field trial again, with a rigorous stats analysis. And ultimately what was shown was that all of the agents tested, the oil blend, the oil-water blend, the beer, and then the control, the oil-based blend was shown to be the most effective by far. It was much more effective than beer. Again, looking at that 80-20 rule, starting at 80% here, tracing horizontally, and then down vertically, the oil blend and some of the oil-water blend, 20% of this accounts for 80% of all the beetles captured, showing its efficacy. So the conclusions from phase 2 were ultimately that this oil blend treatment was extremely effective by a large margin. This oil blend was 5 times more effective than beer and also half as expensive. So both research goals were accomplished. Now, I'd like to share this project with you. This is the project that I'm currently working on. It's what I conducted this year. There aren't official results released yet, but I'd just like to touch upon it as I think it's exciting. So phase 3, or year 3 of my project, is where I took this blend that I synthesized in year 2, and I'm basically testing it against the gold standard chemical treatment, Comaphos, to basically see what their efficacies are in a neck-and-neck field trial in a field setting. So I'm basically comparing a highly effective organic agent and a chemical treatment against one another in the field. And so Comaphos is applied as a strip inside of the colonies. The strip is cut in half and then stapled onto cardboard with duct tape on the backside. So this is how the label instructs to use Comaphos. The organic agents were obviously placed in the beetle blaster traps. So how I ran this trial was with 24 total honeybee colonies. And I had 2 clusters. So I divided those 24 colonies into sets of 12. I had 12 hives which had just organic agents, and then I had another set of 12 hives that had organic agents and the Comaphos. So in this way, I was basically able to see how the organic agents were doing by themselves, and then how the organic agents were doing with the presence of Comaphos inside all of these hives. So every single one of these hives in this cluster of the organic agents plus the Comaphos had the Comaphos inside of them. And basically this way, it was a neck and neck trial to see how that cobophos, that chemical, was affecting the capture of the beetles inside of the traps. And ultimately what I saw was that while having cobophos inside of the hives, even with the oil blend, the blend's capture did not decrease. So what I proved was that the blend of the cobophos actually had very similar efficacies inside of the hive. And this was a very exciting research finding. The blend is also 80 times cheaper than cobophos per hive. So again, these results aren't official yet, but I just wanted to share these exciting findings with you. Now, unfortunately, that blend isn't available anywhere as of yet, but the best thing that you can use for your small hive beetles is beer. Beer does not harm your bees in any way. You will not end up with any drunk bees using this. And beer can be used not only in beetle blaster traps, but in any in-hive trap as an attractant. Beer is also very cost effective and highly effective for small hive beetle capture. As I showed here with this Walmart comparison, beer is a third of the cost of apple cider, and it was also shown to be 33 times more effective. So the key takeaways for small hive beetle management are really to have good apiary practices, maintaining cleanliness, having adequate sunlight exposure, not adding too many frames or supers, and only adding as many as your colony needs, and then using treatments to treat for your small hive beetle infestations, whether that ultimately be, it's up to you, chemical or organic-based treatment agents. And it's really the synergy of these two, good apiary practices and the use of treatment, that reduces these beetle populations to a low and manageable level. These are some resources that I'd like to share after the presentation. Maybe these can be circulated amongst you all. These may be helpful. The first is a comprehensive overview of the small hive beetle. The second is also another PDF on small hive beetles and their management. And the last link is to the UF Honeybee Lab. This is a YouTube page which has a bunch of helpful videos, not only on small hive beetle management, but just beekeeping tips in general. So as mentioned at the beginning of this presentation, I recently published a children's book. It's called The Bee Story. If you are interested, this is the QR code. If you'd like to check that out, I'd greatly appreciate it. So I'll leave that up for a second.
And if you Google The Bee Story by Atreya, and it pops right up on Amazon. There are two that pop up. One is sold out. Look for the other one. Is that correct?
Yes, sir.
Okay. This is a really good book. I have 6 copies so far that I've been dropping off at libraries and schools. If you have any kids in your life, grandkids, it's a great gift. There's a little something for everyone in there. And I actually learned for it right here. A meteorologist. That's correct pronunciation, Atreya?
Yes, sir.
Meteorologist. The term for someone who studies bees. I knew about entomologist. That was a new one to me.
Yeah.
So it's a great book. It's under $7 with from Amazon. Help Atreya out. Buy a copy, buy several, and go back and give a review then too, please.
Okay,
Anything else?
so I
You're
am now
welcome.
open to questions.
Does anybody have any questions?
Does anybody have questions? If you want to unmute yourself, we can be civilized.
Atreya, I have a question. Did you consider using in your field studies the efficacy of Swiffer pads?
I have heard about that, using Swiffer pads on the top of the colony to treat for these beetles. I haven't actually personally experimented with that. I have read some literature on that. I can definitely share that with you, but that would be interesting to see. Personally, I haven't tested that.
Thank you.
And what about where do we place these beetle blaster traps?
Right, so these are placed in between the frames, and generally I place it in the very first super at the top. The reason for this, you may be thinking, why not place it in the brood chambers? The reason for this is because these beetles actually try and escape the bees. So they're trying to get as far away as possible, trying to lay their eggs. And the top of the colony is where the least bees are. So this is generally where they tend to hide, and it's the best spot to capture these beetles. In fact, if you pop open the lid on one of your supers and you have a decent amount of beetles, you'll actually see some beetles crawling around on the lid.
And I think it's wonderful that we don't have to put oil in there. That's what I was taught years ago. The oil. What oil are you using in your cooking and your blend?
So that was soybean oil. So again,
Soybean
a
oil?
vegetable oil.
Okay.
Yes.
So no matter how many supers you have on, you put it in the top?
Yes, sir. And if you had maybe 5 or maybe 4 or 5 supers, or 4 or 5 boxes rather, 2 or 3 supers, then you could add one trap into the very top super and then 1 trap in the second super.
In between which frames do you recommend?
So generally you can place it in the middle frames, right in the middle.
Atreya, it sounds like you are switching the solution, whatever you are using.
I'm sorry, you didn't catch the question.
Joe, we've lost sound.
Whoops.
Come back soon.
Okay. Has any guys yeah.
We can hear you.
Try it now.
Okay.
I think your microphone's in your headphones.
Okay, are you able to hear me now?
Yep.
Joe, we didn't catch your question.
Yeah, I think I need to.
No, you're good now. We can hear you now.
Oh, okay.
Your microphone's in your headphone.
I
Headset.
know. Okay, I was curious. Since you were during your experiment, you were switching the solutions on a weekly basis, just because that was your study design. But in the field, if we were using it in practice, would you recommend switching the solution weekly? Because it's, I guess the volatiles will maybe decrease in intensity. Is that necessary, or don't you know?
Right. So another issue with that is actually as these beetles die inside of solution, that odor of their decomposing bodies actually decreases the attractiveness of that solution inside of the trap. So generally having that treatment solution just be there in itself for more than a 2-week or maybe 3-week period at max wouldn't do much better. So having it at a maximum of 2 weeks or 3 weeks and then changing it out would probably be the best course of action. To counteract that, actually, in my blend, what I did is add one of the volatile compounds that I used, isoamyl alcohol. It actually slows the decomposition and decreases that odor. So it's actually very effective for increasing the lifespan of the treatment. But unfortunately, with the beer itself, treating for more than 2 or 3 weeks wouldn't be very beneficial.
Thank you. I'm curious about another aspect. If I heard you correctly, in order to test how the hive beetle was responding to your different volatile blends, you cut the antenna off the beetle, and then how does the antenna respond? What were you looking for?
Yeah, absolutely. I'm happy to go to that. That's actually
That
one of
sounds
the
fascinating.
yeah, it's a very interesting and also tricky thing, because dealing with these small hive beetles, they're like 4 to 6 millimeters in length, right? Very tiny. So I was doing these excisions under a microscope. It's like neurosurgery, but on hive beetles. And so once you extract those antennae, they're live from anywhere for 3 to 5 minutes. So time is really of the
No
essence of this
kidding.
process. Yeah.
Hmm.
And once you put them onto that electrode, how it works is once the volatile is introduced, there's a few components to this setup that I'll just explain briefly. So the first thing here with this red arrow in the top left is the electrode. So we're placing that antenna onto the electrode with electroconductivity gel. The second thing is this filter paper with the volatile compound. So that filter paper is dipped inside the volatile compound, rolled up, and then placed inside this glass tube. Then the third thing is this other tube that's connected to this volatile, and that runs through to a foot pedal. So whenever that foot pedal is pressed, air is pushed through this tube, and it carries the volatile odors through this tube and then onto the antenna. That antenna picks up the response and then transmits it to the electrode, which then amplifies it and then runs it through to a personal computer. And on that computer, there are readings that are generated. Basically, there's a baseline, and then that electrode is able to see how the beetle is responding. So there's like spikes, peaks that are shown, basically showing the strength of the response. So if the beetle responds very strongly, the peak will be very fast and very high. And then based on those responses, you can see, how the beetle is responding to the compounds.
Thank you. That's incredible.
Thank you. Hope that was helpful.
Oh, yes. Interesting.
Those little
Let me ask-
mini beetle blaster traps you had, is that a research item or where'd they come from?
Sorry, could you repeat that? The first part of
The-
the question cut off.
The little mini beetle blaster traps that were about 3 or 4 inches long.
Mhm.
Is that a research item?
Yes, sir. So this was funded for by the USDA.
Okay. But I mean, the beetle blaster traps we get are 8 inches long.
Oh, okay. So this was the mini beetle blaster. This is 6 inches.
Okay.
Mm.
And the higher the alcohol in the beer you found worked better?
So I didn't actually evaluate the different alcohol concentrations in the beer. The hypothesis is, and this is actually, I'd like to take a moment to explain why I think beer was doing so well. So that yeast that I mentioned earlier in the presentation, Cottima omeri, it does fermentation inside of a colony and produces that alcohol, or that volatile compound, isoamyl acetate, right? And acetate is a derivative of alcohol. So essentially, beer is produced through alcohol fermentation, just like that volatile compound, isoamyl acetate, is produced by the yeast inside of the colony. And that isoamyl acetate is attracting other beetles in the vicinity of the colony. Similar to that, since beer is produced through alcohol fermentation, it may be mimicking that isoamyl acetate, and thus increasing your alcohol concentration could result in, more beetle attraction. So that's an interesting hypothesis to explore.
I'll try that this summer. We have some high alcohol Canadian beer up just to the north of us.
Yeah, I've heard a lot of times people have called this Miller High Life garbage, which obviously I haven't tried it. I'm underage, but maybe increasing that alcohol concentration could have some effect. Are there any other questions?
Yes.
Yes, sir.
Have you noticed if there's a difference? You say that the beetles go to the larvae, or the beetle, the adult beetle, I guess, goes into the dirt and then pupates. Would you say that it would slow that down to use solid bottom boards, or does that make a difference?
So you're saying that if you place solid bottom boards or like concrete in the vicinity of the hive, that it'll prevent them from digging into the soil?
Yeah, that was a question, because a lot of folks like to use screen bottom boards. I'm just wondering if a solid board would cut down on their getting into the soil and mating or whatever it is they do.
So they tend to crawl out from the edges of the hive. I'm not exactly sure if they can fall through from the bottom. So I'm not sure if using a solid board would make a difference, because I'll share one story with you. One of my research mentors was working in Africa, and he was doing some work with small hive beetles. One morning when he was rearing some beetles, and then one morning when he came in, he saw that the door had been left a little bit open, and through that door there were larvae that were actually crawling through from the ground, from the bench of the laboratory to the ground, and then making their way down the stairs and outside of the building to pupate in the soil. So they can travel very far to pupate in the soil. Some people recommend placing concrete or grain or any sort of material in the vicinity of the hive to try and prevent those beetles from pupating, but they tend to crawl and then make their way into the soil somehow. So targeting that pupal stage is something really difficult to do. A lot of people use that soil drench, and it is limited in its efficacy, but you have to use a lot of it, and you don't know where you're treating or what you're treating for exactly.
So you're in Jamie Ellis's lab?
Yes, sir.
So there was no difference in the efficacy because of the effervescence of the beer, the carbonation in the beer didn't have any effect on your overall results.
So is that referring to the phase 1 or phase 3?
Yeah, the phase 1 when you were using beer as one of your test samples when you were doing the 7.
So sorry, could you repeat your question?
Well, I'm saying I'm just wondering if the effervescence of the beer had any effect on maybe dispersing the volatiles in the beer or making it more of an attractive bait than some of the other samples that you used.
Oh, yes, I understand. Thank you. So I definitely think that the effervescence and particularly the volatility in the beer. So beer is very volatile. 90 to 95% of beer is water-based, right? So it's easily evaporatable, and therefore its odor can spread very easily inside of the hive. And this may have been a reason that it was so effective. And so likely I believe that played a role in its attraction.
Mm.
I noticed in this slide that I guess the traps are set on more or less on the edges rather than the middle. Can you comment on the difference between what you were advising, put the trap in the middle as opposed to there on the side?
Right. So there's no major difference, at least from what I've observed, in placing them in different locations. I've always placed them in the center for purposes of consistency. Generally, if you place it on the side or like 3 frames away from the center, or you have 2 on either side, there's no set practice. This could be something you could do, placing 2 inside 1 super if you have a colony that's extremely weak. So here, I'm not sure how many supers were used in this image. This wasn't an image that I derived, or that I took. It's from the internet. But this could be like this sort of setup could be used in a colony that's pretty weak, something that has a lot of beetles in it, 2 large traps in either side to try and really control for these beetles. But ultimately, there's no correct way to place these traps. Generally, what I did again is having 1 trap in the top super and then 1 in the second super, both in the middle.
Thanks.
Of course.
Hey, you had mentioned diatomaceous earth. Are you talking about like underneath the hive? So if I put a layer of diatomaceous earth on my concrete underneath the hive, is that gonna cut those up as they drop out, or is that not gonna affect them?
Yeah, so you'll have to place it on top of the concrete rather. It'll be placed, and then whenever they come in contact with that diatomaceous earth, it'll just dry out their cuticle. So yeah, after they fall out, it will kill them.
How thick of a layer would you suggest to be of any use?
I'm not sure. I don't want to give you an incorrect answer on that. I don't have much experience using diatomaceous earth. If you'd like, if you'd like to share your email or shoot me an email, I have my email listed on the last slide. I can look into the literature on that and definitely share some resources with you, but I don't want to give you an incorrect answer. I don't have much experience in that. Sorry. This is my email. I'd be happy to look into that for you.
Very good, thanks.
Any other questions out there? Atreya, thank you very much for your time this evening. And again, folks, go out there and buy his book for your kids and grandkids and neighbors' kids. I'd hand it to us. I'd appreciate it. He would too.
Yep, thanks a lot.
We've been
Thank you so much.
Thank you,
Yeah.
Atreya.
Thank you.
we've been recording this meeting, and Leslie and Atreya and myself, Atreya taught me how to load this up to our Zoom meetings, up to a YouTube channel. So if you go online in another day or so, Leslie will send this out, but we should have this up on the Windham County Beekeepers YouTube channel.
Hey, Atreya, keep going on this, man. That's really fabulous. We're very appreciative.
Thank you so
Okay,
much,
we're-
sir. That means a lot. Thank you.
Yeah, I really do expect to see you out there. You're the up and coming star. You know, it's James too, and Dewey Corone, they're getting old.
One last thing. I do have a short survey. It's 2 questions. This is the QR code for it. If you don't mind pulling out your phone and just filling this out, this is really helpful to me. It's just feedback on what you thought I could improve on my presentation, on my PowerPoint, or also my speaking. It's really very helpful. So I'd be grateful if you could take a second to fill that out. Thank you.
I'm on a flip phone, so I can't, but I think you did a very good job.
Thank you.
Definitely.
Outstanding.
Thank you.
Like spring might be here with the weather, folks. Looking forward to seeing you all Saturday at the Newfane Library. And that's one of the libraries your book's at, Atreya. That's the Windham County Beekeepers Home. We've been there since we began. Guess nothing else. I guess we're going to be calling this a night, folks.
All right, talk to you later.
Today, enjoy. We can
Thanks for
stop
setting
show.
this up, Jeff.
Thank you.
Thank you once again.
Thank you all so
Good night.
much. Good night.
Good
Be
night.
well, everybody.
I'm gonna try this again.
All right. Thank you so much. Good night, sir.
Thank you, Atreya. I'm going to be, we'll be sending you something down to Orlando here real soon.
Oh, thank you so much.
Get you
Bye.
some maple syrup from Vermont. Good night. Thank you.
Thank you.